Bitcoin's programming language can loop. It can store a variable. It would fail any introductory computer science course, and that is precisely why it works. This deliberately crippled language is what lets tens of thousands of computers around the world agree every single time on whether a transaction is valid. To see why this works, start with the two questions every Bitcoin output has to answer. When Alice pays Bob, the coins she sends become a UTXO, an unspent transaction output sitting on the blockchain. That UTXO must specify two things. First, authorization. Who is allowed to spend this? Second, authentication. How does the spender prove they're that person? Both questions are answered using the same tiny language called script. The output script encodes the log, the conditions for spending. The input script, supplied later by the spender, provides the key that satisfies those conditions. Script is a force-like stack-based language. A stack is just a pile of values where you can only touch the top. Two operations matter. Push adds a value to the top, pop removes it. Script executes left to right. Each token is either data which gets pushed onto the stack, or an operator which pops some values, computes something, and pushes the result. That's the entire model. No variables, no memory, no jumping around, just a stream of tokens consuming and producing values on a single stack. Let's run a real script. The tokens are 23 OP underscore ADD, 5 OP underscore equal. First token 2, push it onto the stack. The stack is now just 2. Second token 3, push it. The stack is now 2, 3. Third token OP underscore ADD. This operator pops the top two values, adds them, and pushes the result. 2 plus 3 is 5, so the stack becomes just 5. Fourth token, 5, push it. The stack is now 5, 5, final token, OP underscore equal. Pop the top two values and compare them. 5 equals 5, so push true. The stack ends as just true. The script returns true because the top of the stack is true. That's all validation really is, running tokens through a stack until something is left on top. So why design a language this limited on purpose? The limits are the design. Script is intentionally not Turing complete, meaning it cannot express arbitrary computation. There are no loops. The only flow control is simple conditionals. Why does this matter? Because every full node, every computer enforcing Bitcoin's rules, must run every script in every transaction. If a malicious user could write a script that loops forever, one transaction could freeze the entire network. Bounded execution isn't a missing feature. It's the shield that makes denial of service attacks against the validation engine impossible. Script is also stateless. Nothing persists before execution, nothing persists after. There's no global memory, no shared variables between scripts. Every script runs in a clean environment with only the input is given. This guarantees determinism. If your computer evaluates a script as valid, every other computer running Bitcoin will reach exactly the same verdict. Identical inputs always produce identical outputs. That property, global reproducible agreement, is what makes consensus across thousands of independent nodes possible. Without it, two honest nodes could disagree about the same transaction, and the Bitcoin's shared ledger would fracture. Here's a surprising example. Suppose an output script is just 3, OP_ADD 5, OP equal. Anyone who provides the input script 2 can spend this UTXO. Why? Because when you run them together, you get the same arithmetic we already did, ending in true. No signature required. Anyone with arithmetic skills can claim those coins. This breaks the common assumption that Bitcoin script is only about signatures. It isn't. Most real outputs do require signatures because that's how you prove ownership securely. But the language itself is more general. It validates any computable spending condition. Now, how does validation actually run today? Originally, Bitcoin concatenated the input script and output script into one program and executed them together. This caused a serious flaw, the famous 10p return bug in 2010, which let attackers craft inputs that bypassed checks entirely. The fix changed the model. Today, validation runs in two stages. Stage 1, execute the input script alone. Take a snapshot of its resulting stack. Stage 2, copy that stack into a fresh execution of the output script. Run the output script on that copied stack. If the final top value is true, the spend is valid. If false or if execution fails, the transaction is rejected. That copy semantic matters. The previous output, the UTXO being spent, is never modified during validation. Nodes only operate on copies of its stack state. If a spend attempt fails, the original UTXO is untouched and remains spendable. This rules out a whole class of attacks where malicious scripts try to corrupt or partially consume outputs. It also clears up a common misconception. Scripts don't mutate the blockchain during validation. They run in isolation, return a verdict, and the verdict alone determines whether the new transaction is accepted into a block. The UTXO being spent either gets fully consumed by a valid spend, or it stays exactly as it was. Step back and look at what this design buys. A stack machine with no loops, no state, and a bounded runtime, modest by any modern programming standard, is exactly what makes global consensus tractable. Every node, anywhere in the world, runs the same tiny interpreter and reaches the same verdict. A more powerful language would have been a more powerful weapon, more expressive, but also more dangerous and less predictable. From this primitive substrate, every Bitcoin spending pattern is built. Pay to public key hash, the everyday wallet pattern. Pay to script hash, which lets complex conditions hide behind a short address. Multisig, requiring several signatures. Time locks, which delay spending until a future block. And ultimately Taproot, which compresses sophisticated contracts into elegant single signature outputs. All of it composes from the same handful of stack operations we just walked through. Bitcoin doesn't validate transactions by checking patterns, it validates by running code. And the genius is in how little that code is allowed to do.